Hello everyone, welcome back. So, we will continue the discussion on map based localization. In the last class, I explained the logic of having a map based localization and how we do this map based localization using a two-step process. I mean, two updates, primarily a prediction update and a perception update. So, in the prediction update, we use the odometric information and update the position of the robot, and then at the new position the robot will use its sensors to collect information from the surroundings and use that information to match it with the map information, and then based on this they will actually update the position and its covariance. So, that is basically known as a perception update. So, there are two steps, prediction update and a perception update in map based localization, and I explained how it works, basically explaining using a scenario. I explained how this actually works. So, in this lecture we look at more its mathematical formulations, how algorithms can be used for this matching of the information and then updating the position. So, just to give you update that what we discussed in the previous class. So, we have a position pk, the previous position estimate, and its covariance given. So, the robot is initially at one location and its position pk and its covariance sigma p is known. So, p and sigma p is known, and from this position the robot is given a control input uk and it moves to the new position pk plus 1. Okay, so, this is the pk plus 1 and it will be having a covariance sigma p k plus 1. So, that is basically this one. Okay, so, this is the new estimate that we need to make. Okay, so, we finally need to have the position p k plus 1 and sigma p k plus 1, and to do this, to estimate this position p k plus 1 and sigma p k plus 1. So, finally, when we say localization, we want the robot to know its position and the uncertainty at that position. So, this is basically the localization requirement, and if you have to do this, we need to go through the 5 steps which I already mentioned in the one of the previous classes. But actually you can see here the 5 steps are basically you have a prediction based on the previous estimate and odometry. So, first you use the encoder information and the previous position and get the new position predicted, and then you observe with the onboard sensors. So, you have observation. So, you observe with the onboard sensors, collect the information, and then use the map information and use this information to match the whatever you observe. Whatever is observed is matched. So, measurement prediction based on the prediction and map. So, what actually it says that at a particular position where the robot has reached, robot will predict what it can see, and then it will see what actually it is seeing, and then match these two, and then based on the fusion estimate the new position and then get a new position estimate. So, that is how you get the pk plus 1 and sigma pk plus 1. So, we need to have these 5 steps in doing this. The challenge is basically, okay, how do you actually fuse this information? So, you now suppose the robot is in one location. Suppose this is the arena and the robot has started from here. Suppose there are some features here. So, the robot has actually moved to here, okay, the new position and its estimate. Now, based on the map information, the robot says that, okay, you will be able to see something here, you will be able to see something here, and you will be able to see something here. So, that is what actually the robot will predict based on the observation, based on the map information. If it is at this position, it should be able to see these things. And then the robot will actually use its sensors to see what actually it is seeing. And if they are same, what it is seeing and what actually it is supposed to see, both are same, that means the predicted position is the correct position. The position the robot is reached is the correct position, there is no error. If they are different, or there is some difference between what actually the robot is seeing and what it is supposed to see, there is an error, and that error can be used through some fusion algorithms to correct its position and get a new position estimate, which is the pk plus 1 and sigma pk plus 1. So, this is what actually we need to do in the estimated the localization using map based methods. Okay. So, there are multiple algorithms and multiple methods available for this. We will not go through all the method, but we will just discuss about two methods. One is known as the Markov localization, the other one is the Kalman filter based localization. So, these two are the most commonly used localization methods, which actually uses the map information, and the sensor information to localize. So, in Markov localization, you can see here the localization is starting from an unknown position. So, it can actually start from any position. The robot need not know where it is currently. It can be anywhere in the arena. Okay, you have a room or some other place where the robot is working. So, you want the robot to localize itself. You need not know its initial position. So, completely unknown. So, the robot will believe that it could be anywhere in this arena, and it can start localizing based on that information. And then it recovers the from any ambiguous position, since the robot need not know its current position. But the challenge here is that when we have this kind of a situation, what we normally do is that we actually, suppose we have a room like this, and we want to localize the robot in this room. What we do is we actually divide this into multiple grids. Okay, you can actually have any number of grids, and then say that the probability that the robot is in any grid is equal in the beginning. That is, the robot could be here, 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 or anywhere. So, it is an equal probability. Suppose there is 100 grids, we will say it is a 0.01, probability is 0.01, and the total probability will get 1. So, you will say that it is 0.01 in all the grids. Now, the robot is given a control input ut. Now, based on that control input, it will update what will be the possibility that the robot is here, here, or here, whatever it is. So, it will update the probability of all the grids once the robot starts moving, and then it will look which one has got the highest probability. Based on that, it will find out what will be the approximate position of the robot. So, at every instant, we need to update the probability of all the grids in this method. So, that is one of the difficulties with the Markov localization, but the advantage is that we do not need to know where the robot is. Even if the robot lost its position somehow, or the robot is not completely uncertain about its position, still it can start again and then recover its position. So, that is the advantage. So, this particular one, since you have to update it every time, so the memory and calculation power can become very important, and if fine grid is used. So, if you are using very fine grids, then the update will become very difficult, because you need to have a lot of memory and lot of computation power. So, that is one difficulty with the Markov based localization. So, we will see how the Markov based localization works. But before that, I will just tell you what is Kalman filter localization also. So, Kalman filter localization is again a map based localization method, but it tracks the robot and it is inherently very precise and efficient. It is a very precise and efficient method. The only thing is that we need to know where the robot is currently. If you are to implement the Kalman filter localization, the robot should know its current position and its uncertainty, and then from there it can actually start. A completely unknown position, the robot will not be able to start the localization. So, that is the difficulty with the Kalman filter. So, if the uncertainty of the robot becomes too large, then the Kalman filter will fail and the position is definitely lost. So, you will not be able to recover the position of the robot. So, that is basically the Kalman filter localization. So, this is very efficient, and a lot of practical implementations are there for Kalman filter localization. But Markov localization works for some applications where you do not have too much of fine grid, and still you will be able to computation power is sufficient to get the localization done. Then Markov is a good option, but Kalman filter is the most commonly used, or you will see a lot of literature on Kalman filter based localization. Okay, so let us look at the Markov localization. So, as I mentioned, it uses an explicit discrete representation of the probability of all position in the state space. So, state space basically, if you have an x, y, theta as the robot position, and then for every grid you need to have the x, y and theta for that grid, its probability of that its probability for that grid. So, the probability of all position in the state space is needed with the discrete representation. So, this is done by representing the environment by a grid or a topological graph with finite number of possible states. So, you will have a finite number of possible states like x, y, theta, and then you will have grids which grid or a topological graph, and then you look at each grid and then see what is the probability that the robot is at that location, and what is the probability of its x position, y position, theta position, and then update it at every instant, and then keep on doing this and try to find out at every instant which one gives you the highest probability. So, that is the Markov localization method. And then during each update, the probability of each state of the entire space is updated. So, the entire space, entire grid need to be updated, and for each state. So, you will be having x, y and theta, and then for each grid you need to update all this information. So, it becomes a bit complex to practically implement, but still it's a proven method of localization, and the advantage, as I mentioned, that any ambiguous position the robot will be able to recover. Okay, so to understand the Markov localization, we need to have a bit of background in probability. So, I hope most of you are having this background, but just want to tell you. So, these are the terminology that we may be using. So, PA is the probability that A is true, and PAB, that is the conditional probability of A given that we know B. So, that is known as PA by B, that is the conditional probability of AB. Okay, so, probability that the robot is at position I given the sensor input IT is given as P of RT equal to IT, where we have the probability that the robot is at position I given the sensor input IT. So, we know something, and based on that we can actually get the probability, that is known as the conditional probability. And then there is a product rule, and the product rule is basically A union PAB multiplied by PB, and this Bayes rule is PAB, that is conditional probability of A given the B is known, can be obtained as PB B by A, PA and PB by divided by PB is the Bayes rule. So, this Bayes rule will be used in localization, because we will be using the conditional probability, that the probability that the robot is at a particular position given a control input or a map input, and if we know that, we will be able to use that one that information and the Bayes rule in order to calculate the conditional probability. So, we will be using the Bayes rule for estimating the robot position, and the total probability is given as PA, that the robot is at A is PAB given PB multiplied by PB for discrete probabilities. So, you can actually multiply these probabilities to get the total probability of A, that is probability, conditional probability of A given B multiplied by the probability of B will give you the total probability A. So, that is for discrete, and if it is for continuous, you can go for the integration of PAB to PB, and PB will be the total probability. So, in case the probabilities are given in discrete manner, then you can actually use this multiplication and then the summation over B sigma, or you can do the integration over B and get the total probability. So, this is okay, we will be using the total probability principle and the Bayes rule in getting the map based localization done. So, let me take a example of Markov model localization. So, we do this Markov localization based on two steps. As I mentioned, we will be having a prediction update and then having a perception update. So, prediction update is basically to get the belief bar xt, that is the position of the robot or the belief state of the robot before getting the sensor input. That is the prediction update. The robot estimates its current position based on previous position and the odometric inputs. So, based on the previous position and the control input or the odometric input, what is the new position? That is basically the prediction update. So, the prediction update is the belief bar xt can be obtained as total probability of the robot being at xt provided ut is given and the previous position xt minus is known and the previous belief state xt minus 1 is also known. So, this is the belief state, that is the probability that the robot is at xt minus 1 is known, and then the probability that the robot will be at xt provided the control, given the control input ut and from xt minus 1 from the previous position. If we know this probability and then we know this belief state, and for our all possible xt minus 1, if you sum this, then you will be getting the prediction update. So, that is basically the prediction update without any control, without the sensor input. So, what we do is we look at the possibility that the robot has moved to xt from its previous position xt minus 1 using a control input ut, and then what was the probability that the robot was at xt minus 1, the previous position, and you multiply this and for all possible xt minus 1, then you will get the belief state xt or belief bar xt, which is the prediction update. Okay, if it is a continuous probability, you go for the integration. It is the same thing, only for discrete we use this, or continuous we use the integration. So, what we are trying to do is to find out the new position estimate of the robot at xt or the probability that the robot is at xt, and that is obtained by multiplying the probability that the robot has reached xt with a control input ut from its previous position xt minus 1 multiplied by the probability that the robot was at xt minus 1 in the previous instant. So, these two, if you do multiplication, you will get the total probability belief bar xt. Now, you have the belief bar xt. So, next one is to get the perception updates. So, you have a belief xt now, that the robot is at xt is the probability is known. Now, use the sensor information and update it, and that is obtained by belief xt. So, belief xt is basically belief bar xt, that is the previous estimate position, and then observation zt from xt, that position xt, given the map information multiplied by the previous belief state will give you the new belief state. Okay, so that is how you get it. Sorry, yeah. So, and then there will be an eta. So, this eta is basically a multiplication factor to ensure that the belief state or the total probability is 1. Otherwise, the eta does not have any significance, but it is used to make sure that the total probability is 1, because now we have a belief state xt calculated from the control input. So, that is used here, that multiplied by this probability of the based on the map information, and from xt the robot is seeing the data, or the robot is getting the feature information zt. These two multiplied, these two probabilities are multiplied to get the new belief state, that is the belief xt. So, this is what actually we do in the Markov localization. So, first step is find out all the probabilities that the robot is at xt minus 1, that is belief xt minus 1, then multiply that with the probability that the robot is at xt when a control input is given to the robot. So, that will be the belief bar xt, and then from that belief state, then you multiply that with the sensor information or the probability that the robot is seeing an object zt from the xt, from the current location xt, and that will give you the new belief state xt. So, this is basically the Markov model localization. I will take an example and explain this to you. So, it will be much more clear to you how do you actually get this probability estimate or the belief state. Okay, so general algorithm is for all xt. So when you have multiple grids, so you have multiple grids. So these are all possible xt. So the robot may be could be anywhere here. For all xt, find out the belief state xt, that is the prediction update. So from here, if the robot is here or here or here or here, wherever it is, and it is given a control input of 2 to move forward. So it can actually move to here, or it can move to here, or it can move to here, or it can move to. So for all this xt, you find out the belief xt bar. So you find out the possibility that the robot is here or here or here. You find out all the possibilities because of the control inputs. And then based on the information collected from the sensor, you recalculate the belief states, because now this is known and this will be given by the sensor. So that probability multiplied by this belief state will give you the belief state xt, okay, and then that will be the return belief xt. So this is how you implement the algorithm for Markov localization. So I will take a simple example before we close this session. I will take an example and then explain to you how we can actually use the Markov localization for a practical case. So I will take a very simple case where the robot is actually moving in a one-dimensional grid. So assume that this is the grid where the robot is moving. So I have actually divided this into multiple. Okay. And I will say that initially the robot could be anywhere here. So these are the 4 initial states. I believe that it could be anywhere here in 0, 1 or 2, 0, 1, 2, 3 grids. So I will give an equal probability of 0.25. So as that you can see here, I have an equal probability of 0.25 for the belief state. So the belief x0, that is before we start, the belief x0 is 0.25 for all the grids. So it could be anywhere in the 4 grids. Assume that the robot is moving forward, and we say that the robot is given a control input, and the sensor says that yes, I can actually measure how much is the movement I have made. But then the robot the sensor says that I am not sure how much it is exactly, but it could be 2 or 3. So I say that my measurement says that the ut could be 2 or 3 with equal probability. I could have moved 2 steps or 3 steps, I do not know, but the robot does not know, and the probability is equal probability of 0.5. So there is an equal probability that the robot has moved 2 steps or 3 steps, and that is given by the motion model. So we say that it could be 2 steps or 3 steps moved forwards with an equal probability of 0.5. So that is the Px1 u1 x0. So that is from the x0, control input u1 is given, and it could have moved 2 steps or 3 steps forward. So the robot does not know how much exactly, but it could be 2 or 3. Now, so we have 2 information. One is basically the belief x0. We already have the belief x0, and then we have the probability that the robot has moved 2 or 3 is also given here. From the x0 with a control input, the robot could have moved 2 or 3. So x1, that is the position that the robot could have reached with a control input u also is given Px1 u1 x0. So that is the probabilistic model with the probability of 0.5. It could have moved 2 steps or 3 steps from x0 with a control input. So that is basically the motion model for odometry. Now with these two, we need to calculate what is the prediction update. So the prediction update is basically, so we have now x0 could be from 0 to 3. So it could be 0, 1, 2, 3. So x0 to 0 to 3. So it could be initially at 0, 1, 2 or 3, we do not know. So from 0 to 3, Px1 u1 x0 belief x0, if you get this total probability, that is basically the prediction update belief x1. So what we are doing, we are assuming finding out, suppose the robot was in 0 and it has moved 2, what will be the probability, where will be the robot, or it has moved 3, where will be the robot. Similarly, if the robot was initially at 1 and it has moved 2, what will be the probability that the robot is there, location. So like this, we need to find out the probability of all the grids and find out what is the actual probability. So, this is basically what we are trying to do. Okay. So, what we do? We look at, okay, now assume what is the probability that the robot is at 0. So, that is the belief. Now, I want to predict the update. So, what is the probability that the robot is at 0? And we know that the robot can't be at 0 because the probability that the robot was initially at 0 is 0.25. Okay. And it has, there is no way that the robot could be in 0 because it has already moved 2 or 3. So, the robot cannot be at 0. Therefore, the probability here will be 0. The robot at 0 grid is 0. Similarly, what is the probability that the robot is at 1? Initially, if the robot was at 0, so there are what are the ways in which the robot can actually reach 1? So, there is no way that robot can reach 1 because if it is initially at 0, it would have moved to 2 or 3, and if it is initially at 1, it would have moved to 3 or 4 because of 2 or 3 steps. So, the probability that the robot is at 1 is also 0. Now, what is the probability that the robot is at 2? So, the only probability is that the probability that the robot was at 0 plus the probability that the robot has travelled 2 units, only the way it can be in 2. So, the probability of robot being at 2 is initially it was at 0 and then the robot travelled 2 steps. That is only condition under which you can actually get the robot at grid 2. So, we will try to find out what is that probability. Similarly, we try to find out what is the probability that the robot is at 3, what is the probability that the robot is at 4, and like that we try to find out and get the probability estimates. So, this is what actually we do to get the estimates. So, you can see here now the probability that the robot is at 2. So, the probability that x1 is equal to 2 is that the robot is x0 is equal to 0 multiplied by the probability that control input was 2. So, that was the only condition under which you can be in 2, the robot could be at 2. So, you will see that the probability is 0.125. Similarly, the probability that the robot is at 3, the grid 3 is initially it was at 0 and then travelled 3 units, or initially the robot was at 1 and travelled 2 units. These are the only 2 possibilities that the robot could be at 3. So, we will find out this plus this. x0 is equal to 0, u1 is equal to 3, x0 is equal to 1, u1 is equal to 3. So, probability is 0.25. Same way, you calculate all the probabilities and then you will see that this will be the distribution of probability. So, now belief x1, the prediction update says that the robot could be in 2, 3, 4 or 5 or 6 with a large high possibility that the robot could be at 3, 4 or 5. So, that probability is 0.25, others are 0.125. So, that is belief x1. Now, we assume that we have a sensor and the sensor is measuring some distance from the current position of the robot to this, it is measuring using a sensor. Assume that there is some sensor which actually measures the distance and then give that information as ZT. Says that from my position, I can say that I could be at 5 or 6. So, I am actually measuring some distance from here to the starting position and I am actually seeing it as 5 or 6 units away from the starting position. So, that is the sensor information. So, the probability that it could be 5 or 6 are equal. So, you have 0.5 probability. So, Pz1 at x1m given the map information and the sensor data Z1 says that it could be 5 or 6 away from the starting, okay, and with a probability of 0.5. Now, what we do? We use this information and this information and then find out the total probability for the robot to be in these locations. Okay. So, that is what actually the next step where we calculate the belief stage. So, we want to find out the belief x now. So, what we do? We do the action update. Okay. So, the action update is this belief x1 is there. So, the measurement update. So, action update we already done. So, the measurement update is a rangefinder measures the distance from the origin with a probability as in D. So, this is the probability 0.5. Now, we find out the total probability belief x1 as P z1 x1 m multiplied by belief x1. So, for every probability here P 2, 3, 4, 5, 6, we find out what is the probability. So, we will try to find out what is the probability that robot is at 2, because it was 2. Now, we say that this belief x1, the probability we know what is the probability, it is 0.125, but this one the probability is 0, because it has got only 5 and 6 has got 0.5, all others are 0. So, 2 will be 0, then 3 will be 0, then 4 will be 0, because 5 and 6 only available. Now, we look at this 5 and 6, what is the probability that. So, this probability that the robot is at 5 will be this 0.5 multiplied by 0.25. That will be the probability. Similarly, at 6 also you will be able to get the probability, and then if you do this, you will see that the belief xt, belief at the final belief state of the robot will be like this. Okay, so now if you do 0.5 multiplied by 0.25, it will be a small number. So, we will actually multiply with an eta. So, that we will be actually getting the total probability as 1. So, that is why we use the eta multiplication factor, and then we find that which is the highest probability, and then now we can say that okay, the robot could be in 5 with a very high probability. We can say that the robot could be at 5. The only other possibility is that it could be at 6. So, from this initial uncertainty, the uncertainty has come down and it has become much more clear that it could be at 5 or 6 than 2, 3, 4, 5 or 6. So, this is the way how we actually update the information, update the localization information using the measurement update. So, the prediction update actually showed lot of uncertainty, but a measurement update reduced the uncertainty and gave you much better estimate of the robot position and its uncertainty. So, the position and uncertainty are actually given this. So, this is the basic principle of Markov based localization. So, this can be applied for 3D grid also. So, if you have an x, y, theta and 15 by 15 grid, then you can see that you will need to have a large grid, and then you need to update this x, y, theta for every grid, and then do this computation for every movement. You need to compute the probability for every grid, for every state, and update the database and find out which one has got the highest probability. That will be the position of the robot, or that much distribution you will be able to find out. So, that is the basic principle of Markov localization. Okay, so there are a lot of literature available and textbook also. There are a lot of discussion on Markov localization using topological map. So, you can refer to this, and then if you are interested, you can go through literature, and a lot of resources are available for you to study this. Okay, so we will stop here. We will discuss the Kalman filter based localization in the next class. Thank you.